of how high-performance computing, AI, or machine learning fits into CFD. And I've given my talk the title, The Ingredients for the Next Generation of Flow Solvers. And this talk is intended to be not just for CFD specialists, so fluid mechanics, but also for people from the general scientific computing audience. So we'll not go into too much depth, except maybe for the last 10 minutes, but give you a little bit of an overview of things that you can do. So hopefully it's interesting to everybody in the audience. Okay, let's start. First things first, all of the work I'm showing is not, of course, done by me, but my group. Here you can see a nice picture of them in front of the wind tunnel. And all of the computations that you see are done with our own developed CFD tools, except where I stated otherwise. Let's jump right into it. So flow solvers, I talked about ingredients for flow solvers. So what are flow solvers? I guess we all in the audience know that fluid mechanics plays a role in many engineering and science applications. I've just shown some nice pictures here over on the right-hand side, particularly, of course, relevant to things like climate change, energy generation, energy storage, transportation, and so on, but also, of course, biological flows. And most of you might know that flows are generally described by a system of nonlinear partial differential equations called Canali-Stokes equations, which are shown down here. So we know how to measure flows, how to describe them, how to discretize, we'll come to that later, but how to describe them mathematically. What is fluid mechanics? Well, I'm an aerospace engineer, so here are just a few examples of what we can do with simulation of flows. Here is one example, for example, of an aircraft landing configuration. Here is another thing that we can do with flow simulations. Look into a jet engine and understand how energy is generated efficiently in such a jet engine, for example. So flow solvers are just numerical tools that allow us to predict flows and their behavior, their forces, their effects on objects through computer science tools. So showing you the examples from before, you might ask, okay, if we already have computational tools that can do something like this, why do we need next generation flow solvers? And the reason for that is, from my perspective of a slightly biased aerospace engineer. So why do we need to invest in numerical tools in conjunction with HPC systems that need some form of improvement? Here is my answer. Again, it's a little bit biased. So if you have flown recently, you've probably stepped onto an airplane that looks a little bit like this. That's an Airbus A350, about the most modern plane that we currently have in the skies today. However, if you compare that to an older version, one that initiated the jet age, a Boeing 707, you can see it looks more or less the same. The overall configuration of this aircraft, how we build aircraft, hasn't changed for the last maybe 60 or 80 years. And the reason for that is that this improvement in classical airplane design has stalled. Not just in terms of the configuration, but also in terms of the speed, right? Flying to New York today takes even a little bit longer than it did 60 years ago. And the reason for that is, one part is physics, which I'll talk about in a second, and the other part is also that we lack suitable flow simulators, so suitable engineering tools, numerical solution schemes that allow us to break the barriers of such a design. And these barriers of this design is nicely shown in this plot here. So that's an aerospace engineering specific plot, briefly explained. It shows at what altitude and what speed current aircraft fly. And you can see it's pretty much limited to this nice blue box here. So there's the Concorde, which is of course something that is an extraordinary aircraft, but essentially we have been restricted to this little box here for the last 60 or 80 years. And when you think about that from a computational perspective, that's kind of a nice and comfy place to be, because we are in what's called a linear regime, meaning that you change some flow configuration slightly, and then the output of your system, the solution of your PDE, will also change slightly. So that's to say, we have a good understanding of cause and effect, This linear regime also means that small errors in our numerical predictions do not matter so much. Also, the flow there is steady, so it's statistically steady, meaning that we can actually use iterative solvers to solve the flow in a steady state. And it's, well, essentially, that's maybe a little bit more for the specialists, it's essentially we can do away with single physics, so just consider the flow, and we can pretend that our wings are essentially 2D wings, so we can always compute, from an HPC perspective, problems that have a periodic direction along the span. So all this makes this very comfy, if you want, for numerical methods. However, this is a map, a screenshot I took from the Library of Congress, and I don't know if you can see it, but when people used to draw maps and they didn't know what lay beyond a certain region in the oceans, they would put the label, "Here are dragons" there. And this is precisely what we are dealing with in aircraft design. These pink boxes that I've shown here, they are essentially our dragons that we have to deal with. So they are what I call the nonlinear unsteady multiphysics monsters. So as soon as we try to leave this nice blue box here, we encounter physics that are completely governed by nonlinearity, by unsteadiness, often also by multiphysics phenomena like fluid structure interactions. So they are very much outside of the comfort zone of our classical established computational fluid dynamics solvers. So that's essentially my punchline. If we want to venture into these waters here, so if we want to build radically new aircraft that are faster and more efficient, more ecologically friendly, we also need new computational fluid dynamics solvers. That's what I'm working on together with my group. This is hopefully also highlighted when you just look at, just by visual impression, novel concepts that people are trying out, what new aircraft will look like. You can see here, they look nothing like the aircraft, very far away actually from the aircraft that we are usually currently used to. So this also tells us, okay, the aircraft will look radically different, meaning we will need to adapt our simulation capabilities to these new configurations as well. And even if we stay with traditional designs and just look at something like, can I fly a helicopter, just like this one, not with conventional kerosene, but for example with hydrogen. It's called a blue copter because it's driven by hydrogen. How does hydrogen combustion, does that actually change the exhaust? How does that change the interaction with the tail rotor here? How does that change the acoustic emissions? So already just sticking with designs that we currently have, but going towards ecologically friendly apparatus that already also pushes us outside of this comfort zone of established PDE solvers for steady systems that we are used to. Okay, so that's just an overview of the need for new CFD, for new computational fluid dynamics mechanisms, algorithms, and solvers. And I want to now go a little bit, since this is an HPC focus or a computational science focused conference, I want to go now a little bit deeper into the challenges that come with this task that we have set ourselves. Okay. The first one is, if I want to compute such a flow that is governed by nonlinearities, a high degree of unsteadiness, I need numerical schemes that can actually do this efficiently and accurately on high-performance computing systems. So one example of this challenge that comes with designing such schemes is shown here. We see a simple flow over a cylinder. It's a supersonic flow. You can see the flow, what the flow looks like here on the left-hand side. So you can see it's kind of nice and unsteady and many vortices appearing there. But what I want to focus your attention on is on the right-hand side, because this is what goes on under the hood of our numerical solver, right? In the top pane here, you can see how we adapt the discretization to the underlying physics. I'll talk about that later. Maybe for you just to have in the back of your mind, if you want to cover, if you want to resolve different physical entities like shockwave, turbulence, vortices, you need to tailor your numerical scheme specifically for that physical phenomenon. So the numerical discretization should fit or respect maybe the physical phenomenon you are capturing all of its properties as best as it can. So adaptation of the discretization to the physics is one key. And the second challenge is, of course, how do we do this on an HPC system? So how do we load balance the different adaptive discretization operators to make it an efficient scaler? So this is what you can see on here, different loads of different elements per processor that we distribute as my discretization operator here adapts. Because if my discretization operator adapts, then also the local load on each core will adapt, and that needs to rebalance. So that's one challenge. The second challenge is we will have to deal with multi-physics problems. Here's an example. That's a droplet being hit by a shockwave, and how this water droplet or kerosene droplet and how this droplet deforms is of great interest, for example, in a combustion chamber, right? Because if the droplet deforms, its evaporation characteristics change drastically. So multi-physics, how can we predict multi-physics flows? How can we again have this efficient scheme that can go through multi-scale problems, but also deal with multiple physics with different time scales, with different physical properties, with different types of equations describing the underlying physics. It's another challenge. Just want to look again at the code. This is a little bit of a partner slide to the one we've seen before. Here is this droplet. You can see its shape here in this black line. Here in the bottom is this adaptive discretization that I talked about. So how do we capture the droplet interface? How do we capture shockwaves? How do we capture turbulence with which discretization operator? And in the top part, you can see the load balancing with the MPI boundaries in these white lines here, and the local computational load in the color scheme. So it's just a visualization of how complex building such numerical solvers, not just from a physical standpoint, but also from a computational science standpoint can be. The next challenge, I'll just touch upon that briefly, is uncertainty and sensitivity. So all of these physical regimes that I talked about, as soon as we leave this blue box we saw before, we are entering this regime of high nonlinearity, meaning also high sensitivity to uncertainties, for example, in our initial and boundary conditions. Here is a nice example that we did a while ago. We wanted to predict icing on an aircraft wing, which can lead to a stall and then a crash of such an aircraft. And how can we make safe predictions, reliable predictions, if we have just essentially a myriad number of icing buildup? So the challenge is, how can we make reasonable predictions about uncertain and highly sensitive nonlinear processes? Just one example to highlight the difficulties. You can see that here is the nose of this airfoil. The black region here is this ice buildup. And you can see just by visual inspection how different the flow looks like depending on what shape of the ice is, and how do you deal with this uncertainty under such conditions. Okay, and lastly, all of these computations they require HPC systems. Actually, when you look at our supercomputer in Stuttgart, about 60% of the overall compute time actually goes to computational fluid dynamics and goes to solving such type of problems that I described. So the whole supercomputer, 60% done for these type of simulations. And the reason for that is that fluid mechanics is essentially a great example of extreme multi-scale phenomena. I'll show you one example that hopefully gives you a feeling for this multi-scale character. Here is a transport aircraft, like you've flown on before, I hope a number of times. Here is the main wing. You can see the wing wake, so the flow coming off the main wing, and you can see that it hits this horizontal tailplane in the back. Horizontal tailplane in the back, that's for essentially keeping the aircraft maneuverable. So you want to have a defined, well-defined, and well-understood flow here over this horizontal tail plane. And with wing weight here, which is already highly nonlinear, unsteady, pretty chaotic and wild, what happens if that hits this horizontal tail plane? How does that affect the flow here and then the overall safety of the aircraft? I want to show you now why this is an extreme multi-scale problem. So we'll just focus on this tiny wing here in the back. Okay? So this is what the computational grid for this tiny wing here in the back looks like. This is the setup. That's the main wing. Here is the wing in the back. You can see how fine and complex the grid already is. And here is one simulation of this tiny wing. And I now just want you to look at what happens when I zoom into this flow field. It's a turbulent flow, so that's a nice expression of this multi-scale character of this problem. You can just zoom in and keep zooming in and keep zooming in. There are still new structures that you discover. So still new scales appear in this physical system. So this is clearly a multi-scale problem. When you're looking at now maybe a millimeter on this tiny wing, right? And what you actually would need to resolve computationally is the main wing, like the 10 or 15 or 20 meters from the main wing to this horizontal tailplane, and then the flow on this horizontal tailplane. So, and why is that important? Coming back to one of my previous slides, this is important because such an interaction, the one that I showed you, that actually is one of the limiting factors that limits us to this blue box I've shown before. That prevents us from flying faster and flying more efficiently because we have not fully understood what is happening, what's going on here. And you can see that what's happening to this tiny wing, so this is again the orange box here, shown here in this computation. You can see that this is pretty wild, pretty chaotic, clearly nonlinear, and clearly an HPC type of problem that we need to solve. So by being able to do these large-scale computations, we are able to predict what type of flight situation might occur that is right at the boundary of this current flight envelope, and then currently prevents us from building more efficient airplane. So hopefully and by the way, this is a 1 billion degree of freedom computation, so 10 to the power of 9 per variable for this tiny piece here. And again, you can see why this is such a multi-scale problem. It would be completely infeasible to resolve a full aircraft with this level of heat. Okay, so that's the why. What are we trying to do, and why are we trying to do it? What are the challenges? And let's now talk a little bit about some solutions to this problem. So how can we build modern computational fluid dynamics solvers? And of course, the key ingredient are modern discretization schemes. Now I'll go into the how do we solve PDEs a little bit. I hope many of you are familiar with the topic. If not, I'll keep it short and painless, hopefully. So, modern discretization schemes, what should they look like? The first building block is, for this type of multi-scale problems, we know that high-order schemes are essentially the way to go. So high-order schemes tell us that if I have smooth solution and a consistent scheme of order n, I can bound the error between my true solution and my approximate solution on some finite grid space in H by some constant C and H to the power of n. That is to say, the higher the n, the tighter I can make this error bound. If you know something about numerical analysis, you are familiar with dispersion and dissipation relations, and you kind of know that if I have a high order scheme, I might get close to the perfect dissipation relation in blue here, or the perfect dispersion relation also in blue here on this slide, depending on how I design my scheme. But the takeaway message is a high order accurate scheme has a tight error bound on a given grid. A visual example, I love that. That's actually from my PhD thesis 10 years or so ago. How to visualize this. So here in the middle, we have some form of vertical flow, turbulent flow, computed essentially with H towards 0. So this is the true solution, quotes. And in the left and right, we have the same flow computed with 64 cubed degree of freedom. So a rather coarse H here. The difference between the two being, this one is a second order scheme, so n is 1, and this one is a scheme of order 16, so very high order accurate scheme. And you can see this just by visual inspection, you can see the difference in the solution quality just from these two pictures, without actually doing an error measure or something like that. Okay, so just by visual inspection, we can see these schemes are much more accurate per degree of freedom, and that's the key point. For a computational science person, I'm storing the same amount of data, same number of variables, the same size of variables, is stored to disk or kept in memory for the left and the right part. The only difference being is how effective, how information efficient, how accurate is each of these variables that are stored into on the disk. And that is something that we can influence through the order of accuracy of our scheme. People, when I talk about high order schemes, they ask, okay, it's accurate, but is it also fast? Here is my short answer to yes, high order schemes can be very fast. In fact, so just for the experts in the room, the squares are the reference solution. Again, this H2.0 solution. The solid line is my 16th order scheme. It takes about 80 hours to compute. And the dashed line here, that's for the same number of degrees of freedom, my second order scheme. So these two, this dashed line here and the solid line correspond to these two images here, right? And you can see this only takes 2 hours, that's true, it's much faster to compute, but it's also much farther away from the actual physical truth that we are trying to approximate. And I can now, of course, do an H conversion series, so make the grid finer and finer, and then I end up with this line here. But as you can see, to achieve approximately in the I norm the same accuracy, I'm at 500 and something hours. So this is the answer to, yeah, high order schemes can actually be competitively fast and much faster than low order approximations. That's not just found by us, that's also found by other colleagues. Here's a JCP article, which just compared this for a type of cylinder flow, the same analysis I did before, just arriving at the same conclusion. To put a number to it, I've shown you this computation before, and I said I need about 1 billion degrees of freedom to compute that with my whole high order accurate scheme. If I were to use a low order accurate scheme, so a scheme that has more numerical errors, brings more numerical errors with it, for the same number for the same accuracy, then with this computation, I would have needed about 250 times more degrees of freedom just to achieve the same number of accuracy. Okay, just this plot from here, just need to do an H refinement of my low order scheme to get approximately to the same accuracy. And just from the HPC perspective, this can make or break you easily, this factor of 250, just in terms of raw data size. Okay. Now, very briefly, there are many ways we can achieve high order accurate descriptions. My favorite one are discontinuous coworking schemes. They have seen a pretty strong interest in the last 10 to 15 years or so. They're essentially a combination of finite element formulation, but with discontinuities at the element interfaces. So they are based on a local L2 projection, on a local ansatz in each element. But then the elements are connected, not with some C0 continuity enforcement like in a finite element, with pure numerical flux like in a finite volume formulation. So when you think about discontinuous coworking and think about what the solution looks like, this is what you have in mind: an element-based discretization, local polynomial ansatz in each grid cell, but jumps between the elements. Okay, I'll skip the derivation. It's maybe not of too much interest to this group here. I just want to point out that depending on how you formulate these types of schemes, you can make them very efficient by taking advantage of tensor product ansatz functions and line-by-line operations, which we kind of borrow from the spectral element community, which gives a specific variant of these types of DG schemes, which for a extension to multi-D, so from 1D to 2D to 3D, essentially this resorts to line-by-line operations and not some volume information. That's for the specialists and some details that maybe we can discuss. So that's the first building block: high order accurate schemes, discontinuous Galerkin schemes. They have favorable properties for compressible flows, advection-dominated problems, and they are great to parallelize from an HPC perspective because, let me go back, because this idea means that most of the work is done by the local projection in an element, and the communication to the neighboring element is done weakly through a surface flux. So it has this nice property of having tons of local work, great for scaling, great for node level performance, and just very minimal communication. Okay, second building block. I talked about for a smooth solution, I can bound this error like so. However, we have many cases where a solution is actually not smooth or not smooth enough. Typical examples are shock waves, which I'll talk about in a second, but also under-resolved nonlinear phenomena like turbulence, for example. Let's stick a little bit with the shock wave, and let's just briefly tell you what we do to deal with such things like shock wave, contact discontinuities, phase interfaces with a large density jump between water and air, for example. There, what we do is a combination of H, P, and what I call D, or discretization adaptivity. You saw this example before for the cylinder flow, how we adapt the discretization to the local physical phenomena. Basic idea goes like this. We have in general in each element a high-order polynomial approximation in DG scheme. If we detect some discontinuity, we would switch to a local embedded finite volume scheme. For this finite volume scheme, on this finite volume grid, we do shock capturing, so dealing with discontinuities through some form of limiting, for example, and then reinterpret essentially our local DG polynomial as the solution of this embedded finite volume grid. So the way this works is we have our grid, we have everything with a high order polynomial, and once we detect some troubles with discontinuity, we then switch locally to this more robust embedded finite volume discretization. We solve this with the associated well-established strategies there, and once the discontinuity has passed, we switch back to a smooth polynomial approximation. There are two ways to do that. We essentially pioneered the switching, where we switch the polynomial, we switch the representation from DG to finite volume. There's Gregor Gassner in Cologne, who does this all in a blending idea. So he has a convex combination of the smooth or the high order accurate DG operator and the finite volume subgrids through some blending factor alpha, and he blends them depending on the degree of smoothness and under resolution. How does this work? How does this look like in practice? Here's one example. The first one here is a forward-facing step. This is the flow solution. And here on the right, you can actually see what we do. So whenever we have a shock wave, we switch to this embedded finite volume grid. That's the black lines. And if we detect that we are under-resolved, but the underlying solution is expected to be smooth, we do a P adaptation. So we increase the polynomial under its degree. And this is, of course, also done dynamically. So that's the first idea, P adaptive DG with finite volume, and the image down here, that's the approach by Gregor Gassner, which essentially tells us, well, if I detect discontinuity, I'll increase this blending factor between the highly accurate and the robust operator to go towards this robust prediction through the finite. Okay, so that's how we deal with adaptivity, adapt to the physics. I think I'll skip this slide. It's mostly what I've already talked about, and we've seen this thing here turn out in a movie as well. What I wanted to briefly highlight is why do we do this very intricate form of dealing with discontinuities? Because most people would say, if you have a discontinuity, why not do artificial viscosity? And the reason why we currently think artificial viscosity type of regularization is not the way to go. Instead, we do this much more complex and involved switching to a discontinuous approximation space to a finite volume scheme. is shown in this comparison here. It's a recent paper. What's nice about this paper, we took many people from around the world, Europe and the US, and we compared our approach for compressible turbulence in this NATO, forgot what's a task force or whatever it is called. So we looked at compressible turbulence, and we wanted to see which of the approaches is actually better in resolving the turbulence, but also capturing the shock wave. And our results are always the one in yellow. Reference is black, and the other codes you can see here. This one is a DLR. This is Stanford, I think. This is Purdue University. And you can look up the other ones in the paper I cited. What I'd like to show you is the reason why we think this type of complex adaptation of the discretization operator to the physics is actually worth it. So black is what we are aiming for with the reference solution. Yellow is our solution here, and the other ones are the ones you see here. Shown here is a measure for how well we resolve the turbulence in that flow field. So that's the measure on the left-hand side. And on the right-hand side, we have the Mach number, so how well do we capture the associated shock. Again, our results here are the yellow ones, and you can see they're nicely, sharply capturing the shock wave. We're not completely oscillation-free, we're working on that, but by far we have the sharpest prediction of the shock wave and the best resolution of turbulence. And the reason for that is that we have this special type of discretization adapted to the physics. All of the other codes here, they use some form of artificial viscosity. I'm not saying that it doesn't work, just saying we see our advantages here for using our more complex adaptive discretization scheme for these types of flows. Okay, one slide about our code, one advertisement slide. So our code is called Flexi. All of the computations that you've seen so far are done with it. It is based on this DG method I've shown before. It runs on HPC systems, and we use it for all kind of multi-physics, multi-scale problems. Besides Navier-Stokes, we can do particle tracking 1, 2, and 4-way Lagrangian particles in the flow. We can slide and move the mesh around with Chimera. Fluid structure interaction is also there. We talked about HP adaptivity, and then some other data-driven stuff, which I'll touch on in a minute, maybe a little bit. So this is my one slide advertisement for Flexi. It's open source, so if you want to check it out, please do so. Okay, there's another advertisement slide, because this is an HPC conference. This is the complete scaling of, strong scaling, of Flexi on Hawk, which is our local supercomputer. It has about 500,000 individual CPUs, and it scales perfectly, which is not surprising, honestly, and it's not that difficult to do with an explicit time integration scheme. DG is a natural scaler for the reasons I talked about. So showing this for completeness, but honestly, it's pretty difficult to not get the DG scheme to scale so well as I'm showing here. What we are proud of is the new version of Flexi, which is GPU-based, which we are currently under heavy development, which also has a very nice, strong scaling performance on the available clusters, and we are particularly happy that we get to compute on Jupiter, which is the first exascale computer in UD, so not too far from, closer to you than to me currently, at the UD Supercomputing Center. Flexi is also a lighthouse code for this specific type of flows, for compressible flows, so everything that has to deal with aircraft and rockets and type of stuff, at the Center of Excellence sponsored by EuroHPC. So, enough of advertisement. Now let's come to the second part of my talk, and I want to talk a little bit about scientific machine learning and how this is an ingredient for these types of modern PDE solvers, if you want. And maybe if you work in a different field, maybe you can still draw some inspiration from what I'm going to show you in the next couple of minutes. I'll not read the definitions of scientific machine learning to you, maybe just give you my 2 cents. What makes scientific machine learning different from machine learning just by itself is that we want to encode some physical constraints, some physical consistencies into our machine learning model and method. And that is to say, our machine learning method has still to work and obey our PDEs that describe what our physics do. Okay, where do I think, this is my personal perspective, where do I think machine learning has its place in CFD? Because there are people who think machine learning will completely replace PDE solvers. There are many people working on that. I don't think that's the case, but I'll show you where I think machine learning can actually help and do us some good. And this is what I like to call the scale gap. So scale gap, we've seen this before with the aircraft and the wing. Here's another example, meaning that I have a wind park here. I want to know where to position the next wind turbine. Where to position the next wind turbine is a function of the flow and the drag induced the weight of an individual rotor. The function of that, or the flow over an individual rotor, is a function of the shape of my actual wing section. And that itself, or how the flow around such a wing section now behaves, is again a function of the smallest structures that occur in such a flow. So clearly, I want to position my wind turbine. What I would have to do is to go down to the scale, to this guy here, to make predictions back up to the chain. So, and if you can appreciate this scale gap, then it's clear that we actually are not capable of resolving this fully without any modeling or without any assumptions, but that we need to come up with some form of an upscaled or coarsened equation. Here's another example. Again, in fluid mechanics, that's not my work, so that's from colleagues, so that's not our code, but the same idea. You want to solve actually the evaporation of water over some hill with trees and stones and whatnot on it. In order to do that, we need to first have a look at how the interface of soil to air, right, and understand how the mass and energy and impulse transport or momentum transport happens in that regime. And in order to do that, we would need to look at an individual piece of earth, soil, and understand how the groundwater behaves in that situation. That's actually not a simulation, that's actually an experiment showing that down here. So again, in order to understand evaporation on that scale, we need to know something about porous media flows on the tiny, tiny scale. So this is what I mean by this scale gap. And to make this a little bit more abstract, we have governing equations that describe the physics at some very fine level. So that would be this porous media flow. And I want to solve equations at a much coarser level. So this can be, for example, the level we've seen here on this soil to air interface. So this is too expensive to solve these equations. Instead, I need to come up with some coarsening operator that upscale my equations to this larger length and time scale. And by doing that, I'll necessarily introduce some form of closure model or scale bridging model that allows me to incorporate effects from the small scale that I'm not going to resolve on this coarse scale here. So this model term here is the footprint of this fine scale information on this coarse scale. Now I can only afford to solve equations on this coarse scale here, right? You've seen how expensive this already is, okay? So that's what we need. There we have these types of models, and usually they are derived from physical principles, mathematical principles, and now recently also from machine learning principles. And this is where machine learning is actually useful. And I'll show you 2 examples. Maybe I'll do 3, running a little bit longer here than I intended, so we'll see how far out. Okay, just before we start, maybe a disclaimer. Already said that people are there are a number of people who are interested in replacing the full Navier-Stokes equations through machine learning. So they are going to predict the solution of a PDE through machine learning without classical finite element, finite difference, or whatever. And there are people like me who think, well, we'll still need to have our PDE solvers, but there are some empirical models that we have for this type of scale bridging that I talked about, where I think a hybrid of classical PDE solutions, classical CFD, and L is actually the way to go. And that's what I want to talk about, so no disrespect to anybody who's doing the former, but that's where I think CFD and L actually shine. I'll show you a very, very basic engineering example, no numerics involved too much. And that is when we talk about particles in a flow field. So the idea of a Lagrangian particle flying through a Eulerian description of a flow field. And very, as I said, engineering example of this is we want to predict the erosion in jet engines. So here's a blade of a compressor in the jet engine. That's a new one. And here's what it looks like as soon as it is eroded. Erosion can happen by sand, it can happen by ice, it can happen by volcanic ash, it can happen by birds being ingested in the engine. So it's a matter of safety and lifetime performance of such an engine. So how do we do this? So what's our approach as engineers and computational scientists? We'll say, well, let's solve this with this Eulerian Lagrangian framework. So let's put particles in our flow, and let's see what we can predict about the erosion happening due to those particles. So what we set out to do was first develop the numerical scheme that allows us to have particles and allows us to have them on high order elements that are curved, so do accurate particle wall interactions, do load balancing for particles, which is completely different for a Eulerian frame. But I don't want to talk about this, just want you to know that this is what we actually spend most of our time on for this particle simulator. But what I want to talk about is where machine learning helped us in this project. And that is, well, you have these particles and they come into your engine. And the first thing they do is they hit a wall. They'll hit a wall, they'll exchange some energy, they'll bounce off the wall, they'll leave some erosion damage there, and they'll just keep bouncing and bouncing through those rotor and stator stages. They are all turning, of course, at an incredible speed, so this is a very dynamic system, and the particle's main interaction with the engine or with the geometry is through the wall interactions, when it hits the wall. Okay? So, what's the problem? The problem is that the modeling of the particle as it hits the wall is one of these scale bridging problems I talked about. Okay? Because what would like to do is, of course, to resolve the particle, resolve this structure, have some contact mechanics taking place, and resolve an individual particle wall interaction. But we have millions of particles in such a system, so we cannot do that. Instead, we need this foursome model. We need some model that tells us particle hits the wall, it's going to fly off in that direction at that angle, and it's going to transfer that energy to the material to cause erosion. And here comes the problem. The problem is that the existing wall models, they do not agree with the measurements that are there. So we did some measurements with people from the experimental side. Just quickly, this is what they measured. This gray distribution here. This is what they measured. These light free distributions, and these orange and blue PDFs are what existing models gave us, right? So clearly, this is just for a single particle hitting a wall once. And now these particles, they go flying, they hit the wall 100 of times. So each hit, the model would essentially give you a cascading error. So here's where we turn to machine learning, right? We thought, well, we have measurements. We can actually derive a particle wall model through machine learning. We can have this scale bridging model that I talked about, and we can do it in a clever way in that we not just stupidly learn some input-output mapping, but we can incorporate some physical constraints into the training process, and the constraints that we included were things like particle will lose energy, will not gain energy as it hits the wall. A particle will not increase its diameter, it will only decrease or break up or keep a constant diameter, but not increase its diameter. So what we did here was to develop a physics-conditioned wall model for these types of particle wall interactions. And the examples are, or the results, sorry, of this trained model are these green curves here, which you see, which now fit actually nicely to the experimental data. So this is one example of how we use machine learning in a very tiny part of our full PDE solver to solve this problem. And what we're now able to do with that is to actually predict the erosion that is happening, that people measure. Here's the measurement down here. We are able to predict, at least with much greater accuracy than before, not still there yet where I'd like us to be, but we're able to predict the type of, or the kind of energy, sorry, the amount of energy actually transferred to the wall and the resulting erosion. So let me see, so the dashed line here in orange, that is our prediction of this erosion. The dashed line in gray, that is what is actually measured in the experiment. And you can see it pretty nicely matches this, the first part and the front part. Still some work to do here in the back part of the blade. And to me, this is really amazing, right? Because we have a complex flow. It's compressible flow. There are shocks in there. There's turbulence. You can see a snapshot of the flow here. Things are moving around, and we're using machine learning just as a helper to bridge this scale and improve the model that gives us this particle wall interaction here. So this is one example of where you can use machine learning in such a modern CFD solver, and this is a slide one of my postdocs made, and I have to show it. Here is again showing all the complexities that go into making such a prediction. Here's the geometry. You can see the turbulent flow here. You can see the particle approaching, how it's reflected off the blade. You can see by this change here in reference system that the thing is actually moving. And here are some of the numerical features or numerical capabilities that we've brought into play here to make this prediction work. And the ML-driven particle wall interaction is just a tiny but important piece. Okay, let me see. I'm running, a little bit late, but I think we started like 10 minutes later. So let me show you the second example. So this was pure subgrid scale modeling through data. Let's now talk a little bit about improving discretization through machine learning. And this goes now to the people who know a little bit more about DG and shock capturing, a little bit more for the specialists. So shock waves are something that, of course, occur in compressible flows. Shock waves, as we've seen before when I talked about how we deal with shock waves, they are different to capture because they're not smooth. So what one would need to do is to do some form of shock capturing, meaning some form of numerical adaptation of the scheme to the shock to capture the shock stably and accurately. But to use this shock capturing mechanism only when you need it to, because it essentially induces or introduces a lot of numerical diffusion into your solution, which you only want at the shock zone. Okay, so when you, so the first step that you do when you want to solve such a flow with a shock in it, you have to detect where the shock is because you want to target your numerical scheme's response to that shock location. And this is non-trivial because it's an empirical approach with many parameters. So if you want to keep a PhD student or a master's student busy, you give him such a problem with a shock. You tell him, okay, find essentially a good set of parameters that nicely capture the shock, and then we'll keep him busy for a couple of days because there's a lot of trial and error in fiddling with these parameters. A lot of empiricism is induced. So what we set out to do is to solve this with machine learning, to offload this empiricism into a machine learning algorithm. And we set out to do the second task, which was not just to localize the grid element that contains the shock, but localize the element on the size, essentially on the scale of an individual degree of freedom. This is now again cool for the high order DG guys in the audience. So since I'm running over time, I'll be skipping some of the slides, and my apologies. What we set out to do is to formulate this as a supervised learning with a multi-scale convolutional neural network. Supervised learning meaning that we, from analytical solutions can can generate training data that contains shocks or is smooth. So we can generate as much training data as we want, so that solves one of the problems of supervised learning. And the multi-scale convolutional neural network is based on the idea that a shock discontinuity is scale invariant. So that means it's independent of how far away or how close you are, how much you zoom in or you zoom out, on what scale you look at to the shock, it's always a discontinuity. It does not become smooth. So this is the basic idea that this multi-scale convolutional neural network that we didn't completely develop it, but we adapted the idea from a completely different application that we use. The training goes like this. We input our solution in a grid element. That's just a visualization of what this looks like. And the output of the training is this specification where in each element the shock is located. So the black degrees of freedom, these are the individual degrees of freedom in each element, they are flagged by our machine learning algorithm telling us, hey, I have detected that there is a shock in this element and precisely where in this element it's located. And this works very nicely. In particular, we don't need any more parameters to fiddle with. Once we have trained it, there is no student that needs to do some parameter fitting. Instead, we can just use this trained grid and just essentially plug it into our PDE solver. All it does, it gives us, or gives the solver, this information here. So just by visual inspection, I hope you can see my mouse, by the way. Here's where the shock should be located, and this is what our machine learned approach now gives us. It nicely shows us where the shock fronts are, gives us continuous shock fronts in each element. And you see as we refine the grid, it's consistently also refines the shock location. And again, from a DG perspective, it actually tells us where in each element the shock is located. So this is something that was not available before we did this offloading with machine learning. So we are pretty happy at this point because it's actually useful for us. We can actually use this to know where the shock is. And now do something about the capturing of the shock. So improve the discretization that targets the shock capturing, or target the discretization more precisely to this location. And the way we approached this here was to target our artificial viscosity to this region. So essentially inform an artificial viscosity operator to where exactly the artificial viscosity should be applied. So maybe a little bit more useful, we actually not just used constant artificial viscosity in each element, but instead we prescribed through radial basis functions a smooth high-order distribution of such an artificial viscosity. So the idea is the following. Machine learning tells me the shock will be located here, and then I'll use a high-order RDF to construct a smooth, continuous artificial viscosity field targeted to this distribution here that allows me a specific application of the shock capturing method just where I need my artificial viscosity or just need my action to take place. So that's the brief overview of what we've done. Just want to show you one result, what this can help you with. So here is the OSHA vortex interaction case, classical case for such for benchmarking such problems, and this is showing in gray. This is showing the actual solution that you're trying to match. And the colors show our solution. Between these colors, everything else is identical. The only difference is how do we target our artificial viscosity. So the orange and the art and the blue and green ones, they are what we came up with. The only difference can be how can we target the artificial viscosity, and you can see clearly that on the same grid, everything else being equal, our approach is much more suitable at not smearing out the gradients too much. And when we look at why this is happening, actually look at the artificial viscosity field able to use here, you can see that they are much more targeted, right? They are much more narrow than the ones that are the current or were the current state of the art a couple of years ago. So this is a much more targeted application of the shock capture mechanism, making use of the information that we got from machine learning. Okay, some examples that this actually works in practice as well. In the interest of time, I think, because I have to leave for this private little bit of an emergency now, so in the interest of time, I'll just switch this example here. And just touch on this one very briefly. That would actually warrant a longer discussion, but just for those of you who are looking into turbulence modeling or know a little bit about turbulence modeling, this is now geared towards the experts in the room. If you're not interested in that or not knowledgeable about that, I apologize. So this is the final example. Again, a video to visualize why we actually should be concerned about turbulence modeling. This is a video showing, again, a modern aircraft. And what we'll see in a second is the size of the computational domain that we can, in which we can solve a flow, a turbulent flow, without any modeling. On a supercomputer with millions of degrees of freedom and with millions of CPU hours. So 3 million CPU hours, that's the number of grid points. And that's the size of the domain that we can't afford to solve without modeling. Okay, so clearly, if I want to know something about the whole aircraft, we'll need to model. The scale gap is clear. This is the level of detail that the Navier-Stokes equations give me. This is the level of scale that I want to actually, that I'm interested in the solution on. And clearly this model term has a lot of things to do. The type of modeling that I'm looking for are large eddy simulation models. So large eddy simulation is the idea of filtering the governing equations, applying a low-pass filter, and then coming up with a coarse-grained version of the Navier-Stokes equations, again closed by some model term here. So this is this M term, this footprint of this fine information I have to discard on the coarse-grained information. There's a lot of theory and mathematics behind that. I just want to leave it at one point here, and that is that one part of this model term actually has to deal with my numerical scheme. And the problem that this is essentially a function of my numerical scheme. And my numerical scheme being high order, accurate, and nonlinear means that I have actually a problem where I need to model something that is not knowable a priori. So that means I cannot formulate some form of supervised learning because I don't know a priori what the target that I should be modeling is. If you're interested in the details, here are some papers, but maybe let me show you. Maybe let me show you it in this video here, essentially. So the type of model that I need is not knowable a priori. If it's knowable a priori, I can learn from data. I can do supervised. If it's not knowable a priori, then I would have to learn from experience. Here is an example. You could not learn what is play Pac-Man. I think you would be hard-pressed to try to learn from data alone. So tell the Pac-Man guy where to go just by giving it images of play states, essentially. That's not possible. What Pac-Man has to do is to learn from experience, just by interacting with the environment and observing what the current strategy is giving. So this is maybe a complex or complicated way of introducing reinforcement learning to you, but I wanted to make clear, before I'll skip to the results already, but I wanted to make clear that in this type of modeling, we cannot do supervised learning because we don't know, because of all the nonlinearities involved, we don't know what the correct model should be. Instead, we have to actually solve or optimize the solution of the PDE itself. Meaning that I have a part that's still governed by my PDE solver, I have some model term in there, and I need to optimize the overall solution of my PDE with the model term in the loop. That's not doable by supervised learning, but by reinforcement learning. And again, I apologize, I'll apply the slides, I'll supply the slides later on, that I'm running out of time here, so I'll skip the details on the reinforcement learning and how that relates to HPC. And I'll just show a single example at the end, which hopefully highlights one capability of this type of machine learning approach. So, what you're seeing here is a turbulent spectrum. So let me maybe go back one slide, 2 slides. We're playing with turbulence in a box here, so very simple toy problem. And we are looking at, what you're looking at when you're dealing with such turbulence is you're looking at the energy distribution over wave numbers, called an energy spectrum. That's the green line that you get from your reference solution. The current state of the art are the orange and blue and pink lines here, and you can see they are pretty far off. And that's, again, the current state of the art. We cannot do better with existing models. And I could talk about the reasons for hours, but I just wanted to show you what we are able to actually do with this type of reinforcement learning that solves or optimizes the outcome of the Navier-Stokes equations with the model in place. And that is the pink curve that you are seeing here, which is essentially the, in my opinion, or from my experience, the best current model that you have for this type of flow by, as I said, optimizing a model in conjunction with the discretization. Shown here, 2 existing approaches, again, the orange and the blue one. This is what we're essentially able to do with our reinforcement learning model. So this is much more complex than what I showed before, where we just use the model of the machine learning to augment some submodels, some terms a priori. Here is we actually solve the overall outcome of the system and optimize the model term as a function of the physics, this green curve here that we are trying to fit, and the pink one is the one that we are achieving. So I apologize this was short, but yeah, personal emergency that takes a lot of time at the moment. So I want to summarize. We are still a long way from actually being able to solve flows over an aircraft, and we are still a long way from being able to have numerical schemes that can help us kind of break this blue box that I talked about, this state that we have been in for the last 60 years or so. But these examples, these tiny examples or small examples that I showed, where machine learning can actually help us to offload empiricism, improve some submodels, or maybe allow us to find discretization consistent schemes. I think that's a pretty hopeful start. My next generation of flow solvers, as a summary, the linear steady problems are no longer the drivers that drive progress. Instead, it's precisely how we leave this area of quiet and go into the highly nonlinear multiphysics regions. These are clearly multi-scale problems, so we need high-order methods that allow us to resolve at least the relevant dynamics there. The scale gap will still remain. No matter how high-order accurate my scheme is, the physics scale gap is always larger than what I can account for. So I'll need some form of scale bridging models. This is where machine learning and CFD can come in. And what I've kind of skipped over was how we can integrate the PDE, the discretization scheme, and the ML